Outreach and Engagement Lead for Future Energy Systems. Anyone heard of Future Energy Systems at the U of A? Awesome. Okay, great. I hope you have. Future Energy Systems is a research program at the U of A studying climate change, the energy transition, and how can we make a difference. We work with over 1,000 researchers, about 200 researchers, 1,000 grad students, and other highly qualified personnel, really trying to figure out how to transition Canada to a low net carbon energy economy. Before we start, I do want to start with a land acknowledgement. So at the University of Alberta, we are on Treaty 6 territory and the North Saskatchewan River territory of the Métis Nation of Alberta. And as we explore energy systems, we want to acknowledge all the communities and peoples that we work with and those that live in the areas, as they are truly essential partners in this work. We are grateful to have the opportunity to work, learn, and live on this land. Now, as I said, we are filming this, so we do want to remind current and future viewers that the opinions expressed by the speaker may not be those of the Edmonton Public Library, the University of Alberta, or Future Energy Systems. And today we're going to dive into why some chemicals last forever and how we can do better with Shira, an assistant professor from the University of Alberta in the Department of Chemistry. So I'm going to pass it over to you.
Thanks, Valerie, and thanks everyone for coming. This is my first time doing a talk at the library, so this is pretty casual. If you have questions throughout, I'm happy for you to chime in. If you have questions, I'll pause at certain points though for questions as well. So for those who, I think some are students at U of A, is anyone like a chemistry? Do you take chemistry, anyone? 101. Great. So I did target this correctly. I was like, I don't want someone in here that's like, I know all these high level things. And did you say you work at the university or you're a student too? Nice. Okay. So everyone's student or student in life. Okay. And I won't say anything crazy, the disclaimer I don't think is needed, although some of my work is maybe controversial. So yeah, I'm Shira Joudan. I've been at the U of A for just over 3 years now. And yeah, I'm excited to talk today. So I want to first tell you a little bit about my group. So as a professor, I run a research program at the university. This is a last year's photo. There's about 13 of us. We call ourselves environmental analytical chemists. That means we study chemicals in the environment, including measuring them. So we want to measure them and understand what happens to them. And this group is made up of me and then undergraduate students, graduate students, and postdocs, so people that have PhDs and are working as researchers. So we want to know what happens to chemicals in the environment. And when I think about that's a really big question, right? So we want to know how human-made chemicals can interface between the ones we emit to the environment and the ones they break down to. I'm going to talk about that a lot today. And I'm interested in how the environment itself can act as a reactor and change the chemicals. And also trying to understand how what we do here in cities like Edmonton both impacts locally, but how these chemicals can move far away to remote regions and have a bigger global impact and concern. So sorry if this text is sort of small. I'm going to talk. You don't have to read anything. I'll just talk. But what we do in our lab informs things like government regulations. So I have a grant from the Government of Canada's Chemical Management Plan. Also goes into things like modeling our exposure to chemicals. And also what I will talk about sort of at the end is can we learn from these bad chemicals to hopefully have a greener chemical industry and the chemicals we interact with are not as problematic. So what this looks like in reality, here's me pretending I'm looking at my students' data. My students do all the work. So this is a photo shoot. Photo cred Carlo. Another thing we do is we make low concentration measurements in the environment to study these chemicals. So sometimes when we study chemicals in the environment, we're not just looking for is it so high that it's toxic? We're measuring at lower concentrations because it can tell us things about trends. So if we want to look from a contaminated site moving further away to a cleaner site, we still have to measure those lower concentrations to say something about the region. And so some of those measurements can be quite challenging. And so my group also really works to get those low concentration measurements where we can say something about spatial distribution. And so that's sort of taking a sample from the environment, whether that's river water or, atmospheric particles that unfortunately we see during wildfire, and measuring things in the lab. The other thing we do to work towards this question is we simulate the environment in our lab. So the environment's really complicated, and it can be useful to study things in a simpler manner to break down the complicated, and so we can build back up to the complicated after. So this photo here, also photocred Carlo, is our photoreactor. And so those experiments sort of tell us, like, if a chemical was in the river and the sun was shining on it, how will it react? Does it break down or not? So obviously that is not a river, but there are different variables we can change and study certain things to build back up to more realistic complexities. And these go hand in hand. So you want to do real environmental measurements and these controlled tests, and then they teach you things about each other. So I want to talk about, this says chemicals in commerce. What does that mean? How many chemicals are on the market, right? Everything is a chemical. So not many chemicals occur naturally. We are made of chemicals. This room has chemicals. But there's about 350,000 chemicals that are sold on the market. So this could be your medicine. This could be, there's probably like 100 components in paint, and they're all different chemicals. So people that are not me, Wang et al., went through all the market and came up with this greater than 350,000. But really, there are only select ones that are problematic. It is a huge task to figure out which ones are causing the problems, because there are real big problems, right? And so I work to that, and many people in my field do. This is not the real environment. This is my simplified environment. But once a chemical enters the environment, whether it's going into the air, the water, the soil, it might stay where it was sent to, but it probably moves, right? And so is that air currents? Is that water currents? Is that runoff of a field? And where it is changes what it can undergo, what it experiences, right? So one thing you can think about is something goes in the water, maybe it sticks to the sediment, right? You can see the little particles in the sort of muddy river stick to that and then settle. And everything, that changes. If it sticks to the sediment, then the fish aren't exposed to it, just the worms that live in the sediment, for example. And different reactions happen in different parts of the environment. So the environment is also like a reactor. Usually when people think of chemistry, they think of pouring things and, a beaker, but the environment is also a beaker in itself. It just has naturally and human impacted reactants. And all that changes where it goes and potential toxicity as well. And so I'm really interested in these transformation reactions, I call them. So oftentimes people think, maybe you think degrading, something's breaking down, but it might not degrade completely, right? We always want something to fully degrade, but what can happen is there might be like one step in a degradation and then maybe it sort of stops. So it's really much more complicated than just going away. What's it going away into? So I'm really interested in that, and this is a really big challenge in the field. So I want to tell you a bit about how we think about bad chemicals and what makes a chemical bad in the environment. And so usually we say, sorry, the colors are a little lighter, that's fine. I'm going to go through each of these and tell you a little bit about what they are and how I've studied them in the past. So the first one is persistence. Persistence means how long does it stick around, right? So I just talked about degrading. Persistence is the opposite of degrading. It's not degrading if it's persistent. And how can we study that? This is, baby Shira over here. This is like 13 years ago or something. So we can make real measurements. This is in a river in Manitoba. During some undergrad research of mine, we were looking downstream of a wastewater treatment plant and looking to see if the pharmaceuticals that unfortunately don't really get removed from the wastewater treatment plant, are they still going down the river? So you can make real measurements from known point sources, so a specific spot where they're emitted, and see if it changes. Obviously, you want it to decrease. This is me in grad school. It was actually a visit to Colorado to do a collaboration. And this is you can see this sort of like silver tube. It's an environmental reactor. So the question there is, if this chemical is in the atmosphere, does it break down? So instead of a beaker, because you're talking about gas, you need like a reactor. And so we put in this chemical we think is concerning, and then we put in other reactants like oxidants, like OH radicals, for example, and we study our chemical of concern degrading, and we look for what it breaks down into. So is it degrading? Then it's not very persistent, right? So in both of these, we can learn about that. Bioaccumulation, this is also me in grad school. This is in Southern Ontario. These are fish I'm holding. It's sort of hard to see. So bioaccumulation means building up in biota. That could be humans, that could be fish, that could be a worm. The thought here is it higher in the living thing compared to its surroundings? So a fish is a really easy one to think about. If it lives in this lake, is the contaminant more at a higher concentration in the water or the fish? If it's higher in the fish, it's accumulating in the biota. That's bad, right? Because now the fish is getting, you can think of it, it has like a higher exposure inside itself than it would just living there. So we don't like that when we think about bad chemicals. Toxicity, I don't study that, but I think people know usually what toxicity is. So actually that one's the hardest to study, I would say. There's so many complexities to it. It's much less yes or no than some of the other ones. I'm not saying the other ones are easy, but it's a lot harder to prove definitively toxicity because, you know, it might take a long time to be exposed to have toxic effects compared to like we know if you ingest like a metal, you might die, like mercury, you might die quickly, right? But there are certain other chemicals that like take 20 years of exposure. Think of someone who smokes, right? You don't die right away. It takes a long time to see those potentially harmful effects. So that's why it's hard to prove these toxicity values as well. Okay, long-range transport. This is me during my postdoc. I was doing work at York University. This is actually on Saturna Island, all the way in Western BC. Very beautiful place. And I'm holding a drill, but I'm installing a sampler. And so what we were looking at there was it's all the way on the west coast. And so it receives air from the ocean. And we were trying to understand if the ocean was carrying contaminants through the air. It gets air from China, actually. So it goes like China, ocean, there. And so long-range transport, that's what I was getting to before. Like, if what we emit in Edmonton, is it going to the Arctic, for example, right? And I'm going to talk a little bit more about these concerns, but I think the first thing I'll say is, if we have long-range transport, we have a global problem, right? And that's a lot harder to deal with. The last one here, I wrote mobile. The M is sort of hard to see. Right now, that's only really being considered in Europe. Canada uses the other things. It's sort of silly because to me, mobile and long-range transport sound the same, but the way they define it is it's actually mobility through soil and sediment. So the concern there is, I think the easiest way to think about it is if it's on a field, does it go into the groundwater? So the concern is movement into drinking water sources. So it's long-range transport is generally like through air, mobile's like to the groundwater. But it's the same idea. The concern is it getting everywhere to a point that we can't deal with this quickly if there is a problem, right? So this is sort of, I'm going to use this theme throughout the talk when I talk about concerns, let's say. I'm already talking for so long. But I think one thing I want you to learn today is like persistence is the key to many problems, right? Because if any of those other issues, like it can't really happen without something sticking around. So if a chemical doesn't break down, it can build up in the environment, right? If we keep emitting it, it keeps building up, and it can be transported these long distances. If it breaks down, it's not going very far. And the concern is like, it's going to keep building up to a point that it might have harm, right? Even if it doesn't earlier, like if we keep emitting something, maybe you've heard dose is poison for toxicity. Well, what about like environmental dose, right? And so we generally, persistence, We don't want things to build up. And so in Canada, we have some definitions about what we have thresholds. So this has nothing to do with what they degrade into, just are they degrading? So half-life is the time it takes for a value to decrease by 2. And in air, the half-life to be considered persistent has to be greater than or equal to 2 days. In water, greater than or equal to 6 months. Soil, 6 months. And sediment, 1 year. Now you may ask, why is air so fast compared to the others? And it's because air masses actually move way faster than ocean currents, for example. So for the ocean to move, maybe some of you have studied some of this, but to move from, I don't know, mid-latitudes all the way to the Arctic is on the order of, I think, months, but might be longer. Don't quote me. But air is like weeks. So this is sort of corrects for that. The air moves faster. And the soil and sediment are sort of similar reasons. The one last thing Canada considers is evidence of atmospheric transport to remote regions such as the Arctic. So this is what I was talking about, long-range transport. I wrote a little disclaimer this is my note. I said, as our measurements get better and better and better, if we can see like everything in the Arctic, is that enough evidence for concern, right? So just something to think about. Our techniques to make measurements are really improving. But this is how toxic substances management policy works in Canada. They need all these studies. It is a lot of effort, and they review, and this is how they will regulate and restrict chemicals in Canada, which is, like I said, similar to other countries, although Europe has that slight difference. Okay, so I've talked about the Arctic. These photos are from my collaborator, Ken Jeffries at Manitoba. And again, getting there means it's a global problem if it's a remote area. I think there's also huge equity considerations, right? If you are living somewhere that is not doing the polluting, but you are receiving the pollution, right? Something to consider. If everywhere is contaminated, how do you remediate once there's a problem? The answer is you can't, right? You have to still prioritize. And the big thing is like, we might not know how harmful a chemical is, but if it's everywhere and then we find out it's harmful, not good. Okay, I think I'm gonna just reiterate this one more time. So if it's persistent, it can travel far. It can build up in environment and biota, right? If a fish can metabolize it, can break it down, it's not gonna build up. But if it's persistent, it could. Harder to remediate, and of course, if we find out it's toxic later, we've got a huge problem. And so I would say there's a potential for greater adverse effects, right? It's not saying there are, it's the potential. And it doesn't comment on how much is there or if it's there. Like, you could have the most persistent chemical in the world, but if you're not putting it in the environment, well then, whatever, right? So it's just a way to think about what's going in the environment. Okay, so in order to understand persistence, I've alluded to this a bit, but we need to understand different environmental processes. So what can break down a chemical, right? Photolysis is reaction with the sun. So some chemicals can react with sunlight, or maybe they react with something else that reacted with sunlight. That's a really big process in air and water. There's photolysis happening all the time. Hydrolysis means reacting with water, so some compounds will do that. And a huge one is biotransformation, so biologically related reactions. This can be microbial, so all those microbes that live in soils, for example. There's even microbes in the air, but soils is the big one. Human metabolism and metabolism in all sorts of different animals. So that's the main way I think of like types of reactions. And maybe to fully degrade a chemical, it's going to react with the sun and then it's going to react with water, right? It's like these complicated systems. And I did just note the physical processes. It can sorb or stick and interact with things like soil, right? That's going to make it not move much. It can immobilize it. And we talked about bioaccumulation. Okay. Any questions so far? Good. Okay. Just chime in if you need. So a question I have, and I'll try to what's how long is persistent? Is it forever is what I'll say. So we do have an international agreement called the Stockholm Convention. It's called on persistent organic pollutants. And there's a number of chemicals that have been put on this list. And the way it works is that countries sign on to the list. Also, I'm happy to share my slides with anyone if they want them after. There's some links within. So it's only true if the countries that sign on follow it. Sort of like if you've heard of the Kyoto or the Montreal. So this is the one for persistent chemicals. And so they are persistent and harmful, like persistent and bioaccumulative, persistent and toxic. So maybe you've heard of PCBs, polychlorinated biphenyls. There's old chlorinated pesticides that we don't use anymore on this list. And there are some PFAS, which I'll talk about after, on this list. So it takes a lot of evidence to put these chemicals on this list, and there are requirements to follow up. And so I know it's sort of hard to see, but there's different annexes. So this one's called elimination, Annex A. This one's called restriction, Annex B. And so one example is DDT. Maybe some people have heard of DDT. It's in Annex B for restriction. And the reason it's not elimination is because it is needed to fight malaria in certain areas. So it's a really important insecticide for controlling malaria. So important that the Nobel Prize in Medicine in 1948 was given for this insecticide. But then it was added to the Stockholm Convention, banned for worldwide agricultural use, but approved to control disease vectors when required. So basically, like when the mosquitoes need to be killed for malaria reasons, there are exceptions. And the issue with DDT is transformation related. So DDT is this chemical structure here, and it has two main processes. So two different chemical reactions that can happen. If you're not used to looking at structures, that's okay, but I'll just point out, you can see here in the center, there's 3 chlorines, the Cl, and you can see here, one of them comes off. So that is called an elimination reaction. That's one of the products. The other one is a microbially mediated reduction. So microbes do this transformation, and it's kicking off 1 chlorine for a hydrogen. These are all persistent, the DDE and the DDD, and bioaccumulative. So they build up in vertebrates. And the one that caused the big problems that made it notorious is DDE. And it led to the thinning of eggshells in bald eagles in the US. And so that was Rachel Carson wrote Silent Spring about this. And you know, talking about toxicity, this is why toxicity is hard, right? It's the transformation product that caused the next generation effects, right? It caused the babies to not be born. So it's quite complicated. But it wasn't the DDT itself, it was the DDT that then transformed to the other chemical, which is why, you know, when we try to think of life cycles, we have to include all of these reactions. It's quite complicated. Okay, I think I tried to make this work. A number of chemicals are regulated due to persistence, but only one class was coined forever chemicals. So has anyone heard that term before? Okay, I see some nodding. I will not go on and on. It's a non-scientific term, okay? I don't love this word, but it's caught on, so I have to use it. The chemicals people are talking about are really, I will say PFAS or per and polyfluoroalkyl substances. And that's what I'm gonna talk about in one way or another for the rest of the talk. The reason they were coined forever chemicals is that some PFAS really don't degrade at all. Like to a scale that, like you can't really give it a half-life. We talked about greater than 2 days, greater than 6 months. Like, well, I don't know, we can't measure it in our experiment. So it's just greater than is sort of, it's like the new persistent is uber persistent.
And that's the original chemical or the products that they're making as they're breaking down? Like the original, it will not break down?
Oh, that's a great question, Valerie. So I will have more.
Okay.
But it's a great question because PFAS is this giant class of chemicals. So some of them just don't break down. And then some of them break down to the ones that don't break down. So yes, I will show you more. Oh, my animations are out of order. That's okay. So basically, PFAS contain at least, you can debate about the definition of the class. I've been a part of those debates. We're not going to do that here. They contain a carbon. So in chemistry, these little juncture points are carbons. We don't draw them because they're just the backbone, with all the hydrogens removed and swapped for fluorines. And so when we say per and poly, the difference is that the polyfluoroalkyl substances have all fluorine, so they don't have any hydrogens left. And what that means in practice is there's no reactions going to happen, because where the fluorines are, you can think of it like a reaction's not happening because they're really strong and persistent there. The polyfluoroalkyl substances means that there's some carbons that have hydrogens on them still. And I realize as I'm talking to you all that you don't know maybe that we just don't draw the hydrogens because they're assumed. So I'm sorry about that. But so the difference is there could potentially be some reactions here. Anywhere you see these long fluorinated chains, you'll see these like repeating units. You can think of it like it's just not reacting there. It's just stable. So in 2018, there was a list compiled where they said that 4,700 PFAS exist on the market, so for sale. Some of these are sold as one chemical, but often it's mixtures depending on the usage. I'm going to tell you more about the usages. Maybe now it's estimated to be 10,000. Again, I don't know what the number is. There's a lot of different chemicals that fall in this class. The reality is that maybe there's like 200 or so that are really being sold, but then they can degrade to other ones. So it's a big number. What I want to get across, though, is that there's really little data on most of them. Their uses, their properties. So even simple things like how volatile are they? There might not be a number for that, which is in the scale of what we want to know, that's like one of the simplest ones. And of course, the environmental effects, because that's an impossible task. So because of that, many jurisdictions, including Canada, are thinking of looking at regulating PFAS as a class because they realize it's impossible to do permutations for each chemical. Oh, that's there too, forever chemicals. Okay, so why do we put fluorine on chemicals? Maybe you ask. It really changes the properties of the chemical. So if you imagine a chemical starts as just like carbon and hydrogen, and then you add fluorines, that's what I want to get across. So the first thing is it can reduce environmental reactivity. So in the black, that's chemistry lingo, octane. Octane has an atmospheric lifetime of about 2 days. So just think of the numbers. It lasts in the atmosphere for 2 days. When you switch every hydrogen for fluorine, 1,000 years. Like, how do you even compare that? This is, of course, an extreme example I'm showing. Also, it can increase the volatility. So this is a C6 compound. The vapor pressure is 0.2 atmosphere. When you fluorinate it, it's 0.3. If these numbers don't mean that much to you, that's fine. But why is it useful? Some applications, we want things to be more volatile. So a really good example of these is refrigerants and heat transfer fluids, for example. And acidity. And so this is more in like industrial usages. On the left is acetic acid, that's vinegar. It has a pKa of 4, which is a measurement of acidity. And trifluoroacetic acid on the right has a pKa of 0. And so I realize these numbers are not that useful. What this actually tells you is this is 10,000 times more acidic because it's a logarithmic measurement. So big changes here. And really that comes down to the fact that fluorine loves to hog its electrons. So if you took Chem 101 and you remember electronegativity, fluorine's very electronegative. I think they teach that in that course. I never taught it. Okay? I think that's 101, not 102. Okay. So I told you this might be a tricky slide. If you don't understand this, it's fine. But I'm going to try because I think you could know. Huge class, PFAS, many chemicals. Can we divide them up into smaller groups that are meaningful? The first one on the left is what I'm going to call a small molecule PFAS. Small molecules include drugs, like pharmaceuticals, pesticides, I think that when people think of a chemical, they think of a small molecule. So one example here is, I've written PFOS. It was used historically as a surfactant, so like a fancy soap, changing surface properties. This is usually what people are talking about when they say PFAS, small molecules. This is what we mostly measure. This is what we study. They're either used directly or they're used to make these other things. The next one, this is my very simplified drawing of it, but I have this ball here, and what I want you to imagine is that these units are all bound to the rest of the polymer. So a side chain fluorinated polymer. So you can see it sort of has this like feature that looks like the other one, but then it's stuck onto something. So these are repeating units on a backbone, so it'll be like this. These are usually added as surface protectants. So if you ever use Scotch Guard, or you buy a rug that says spill proof, or oh, I have something, I think in 2 slides, that is an example. Stain-proof fabrics, all those sorts of things. This is usually what they're talking about. It's really hard to measure these. They're often referred to just by their carbon chain length. So my mom's friend used to sell fabric to Lululemon, and he was like, oh yeah, we can't use C8 anymore. And I was like, oh yeah, that's what you're talking about. So that was like 10 years ago though. And then the third is fluoropolymers. So everyone has heard the word Teflon, I'm sure. Teflon is a brand name for PTFE, and these are more like the hard fluorinated plastics. Probably you've seen some sort of Teflon tube or plastic or bottle or whatever it is. These are usually, people think about them very separately. It's very hard to measure them, and the way they relate to the other PFAS is much less understood. We're working on that in my group a bit right now. So very different, like plastic, surface coating, and then surfactants and direct use chemicals. Okay, so because of all these things, they're used in a lot of different places, and sometimes surprising, because you don't always have to say what's in things. So the properties that are useful are water repellents, oil, stain, dirt repellents, right? So that's why if you're like an easy wear shirt, like no iron maybe, you never know. All these things are like better spreading. So paints had a lot. I think they don't really anymore. And they can also, PFAS can create barriers that are really useful for other applications. So a really big historical usage is aqueous film forming foams, which is a mouthful, but what it is the special firefighting foams they have to use for fuel fires. So at airports, military bases, you know, anywhere where you can't, it's very specialized. And of course, when you have a fire like that, you want to use what you got to use, right? The issue actually for the contamination has been related to the training people have had to do. So if every year you have to spray it directly into the environment, that's bad, right? If you had to use it when a plane was on fire, well, how many airports have a plane on fire? How many times, right? Way less than once a year per location. So this has been a huge one that's actually dealt with much separately than all the other ones, because you can imagine the safety importance there. But PFAS are found in dental floss, right? I don't have a picture of makeup, but makeup as well. And that's for like the really smooth spreading. So I think if you buy I just use the waxy dental floss, you know, that's fine. Wax doesn't have PFAS in it. But you know, have you ever used that dental floss that like glides too smoothly? No one? I've used it. It's like Easy Glide or something. That one, I'm like, I think that one might have PFAS. And yeah, so water repellency. So I'll talk about pans because I think people usually want to know about their Teflon pans. So the pans are the Teflon that I said, right? That repeating polymer that I said is like plasticky, even though, you know, your Teflon pan doesn't look like plastic. Historically, actually, the big concerns with the Teflon pans were that the small molecule PFAS need to be used to make the Teflon. I'm just going to go back for a second. So In the process of making the Teflon, the way they make it industrially, because it's all fluorinated, they need to use special fluorinated surfactants that look like this. And so the concern was actually mostly about these that were left over in the pans. And for the workers at the factories, that was really, really a big concern. So I will tell you this proactively because I assume someone will ask me. And it's being recorded, so I guess I'm saying this officially. I still use Teflon pans. They treat them better, so the residuals are gone now when they make them. As soon as, like, if you've got like a scratch and it starts peeling, get rid of that, okay? That's my advice. You don't have to, well, you don't have to agree with me either, but I personally do not think you have to go out and replace everything. That can be pretty expensive, but as soon as, if you do see it wearing out, do get rid of it. You could just get rid of it because you want to be proactive too. I know a lot of people like the ceramic ones that are sort of non-stick as a non-stick option, but you know, you can use stainless steel or cast iron or whatever you want. So I do use Teflon, but that's a personal choice. I don't buy new Teflon, I guess, is what I would say. Oh, I guess the last thing I was going to say is they used to be used in pesticide additives. So to help the spraying, some PFAS were added. You knew that. So that's no longer allowed in Canada. That was early in my PhD, that became no longer allowed. And one thing I want to point out about pesticides is they're the only things really that we purposefully spray into the environment, right? And so when you think about all these chemicals we talk about, it's like, oh no, did it come out of the factory, or did it, you know, come out of the wastewater treatment plant, or did we spill, or did we? Pesticides are the only things that you put there on purpose. And so whether it's the active ingredient of the pesticide or something in the mixture, there is much more scrutiny, rightly so, on that, right? So that's why it was very quickly no longer allowed, because the purpose was just to spray better. So that, we didn't need that. Okay, so one thing I wanted to say too is that I talked about these side chain fluorinated polymers that are used as surface coatings. They can degrade back into these small molecules. So when, have you ever had like a rain jacket and it's not waterproof anymore? Probably most of us have. That's because the water repellent coating either came off or broke down, right? So I'm not saying this for sure happened. The whole thing could come off too, but it's probably both. And there's been some research. My group is working on this too. It's just some hard experiments to do, frankly. And a big thing I do want to get across here is that when the chemicals are bound to the polymer, your body can't really take them up, right? It's not, we say, bioavailable. But once they're small like this, it's really easy to get into the body. So again, it's one of those considerations where like, actually, I don't think these are very bad, but they degrade to something that's bad. So again, it's that chemistry thought that motivates basically everything I do. Okay, so I think I should have maybe put this earlier based on what we talked, but I love these old-timey ads. So DuPont, which is a big chemical company, well, they've merged and done all these sorts of things for legal reasons, but they used to have this saying called better living through chemistry. And I'll just have my little note, which is sort of hard to see, that says that is not persistent or toxic, right? So not every chemical is bad, but let's not add more ones that are bad. So this is a wonderful Scotchgard ad that is advertising a stain-proof sofa so you can have big parties, right? Never before protection for upholstery. This is crazy. This is a Teflon-coated ironing board so that there's no resistance when you're ironing. That's the point. Smooth. It's from DuPont. Enjoy a totally new experience in ironing. And then finally, this is sort of related, but this is an incredible video. And again, I would be happy to send anyone these. Chlorofluorocarbons, which destroyed the ozone. This is the creator of them, a video demonstrating how safe they are. He drinks them. They are safe. They're actually, the thing about chlorofluorocarbons is they're not toxic at all. They're just terrible once they get all the way up into the stratosphere. But it's an incredible video, and I play it for my third-year undergrad class that I teach. So we don't want these. Okay, so any questions, by the way? Okay, so once, of course, what makes them problematic, I'm gonna go back to my PBT-LRT thing we talked about earlier. I've also alluded to a lot of this, but let's break it down a little bit. So many PFAS don't break down in the environment. They are persistent, P. That's bad. They can build up in concentration. Some PFAS bioaccumulate, B. Also not good, because now animals are getting more exposure, or humans, than just the environment. Yeah, we've talked about that. Okay, they've been detected across the globe, including in remote regions. So that's the LRT bit. Yeah, we know about LRT being bad now. Toxicity, complicated endpoints. There are some endpoints that are well understood now and some that are still being explored. Again, there are so many different PFAS. So it's, the question needs to be a little more specific, but some more common ones are thyroid-related issues, kidney cancers, and immune response effects, I will say. So a whole whack. I guess one thing I'll say too is some of the biggest concern are in communities that are really impacted because they had factories and such there. So I don't want to scare everyone. But yes, real toxicity effects. And so some of you know what these are. I will say this is a never-ending story. Yesterday, I just went PFAS news on Google, and there's just PFAS blood testing, pilot finds elevated levels among Indiana firefighters. Battery chemistry might destroy PFAS, like soil remediation. New facility to remove the PFAS from the drinking water. Actually, that's the same story, I'm realizing now. But another big thing that I want to highlight is Canada released in March of last year the State of PFAS report for our government. And it's a really, really good comprehensive link about what we know and what the government is going to do about it. Some of it is like a little, are you going to do a little more, a little faster? But this is all the information, okay? And they say how they're approaching it, and it's really quite thorough. And I think I'm cited in it once, some of my work, but yeah, I'm cited in it. I'm an expert, I am. So the two most notorious PFAS that people talk about are called PFOA, which I say PFOA, and PFAS, or PFOS. I say them like words. These are the most notorious. So on the top is the chemical structure of PFOA, and on the bottom it is PFAS. Their names stand for perfluorinated, and then how many carbons, and then that this one is a carboxylic acid and this one is a sulfonic acid. And so there are other ones that look like it but are shorter or longer but have the same general structure. They're in the same class. And so what maybe you can even see looking here is there's O's on this side and there's F's everywhere else. The F's create this water repellent and fat repellent chain. Pretty useful, right? And then the other side is a polar head group. So it's just like a soap, but like a souped up soap, I would say. So this side likes water. The other side hates water and oil. And so usually when we think about contaminants, they build up in fat, but actually PFAS accumulate more in protein-rich parts of bodies like liver and kidneys because of these chemical structures. And generally, if they have less fluorines and are shorter, they're more soluble in water. And if they're longer, they can accumulate more in animals. So I've sort of alluded to the fact that some of these have been phased out and replaced. There's a lot we could talk about, but I'm going to start. Also, I thought I added animations on this slide. Oh, whatever. Imagine we don't have any of this here. So I'm going to start. So this is PFOA, and this is PFAS. And if this is a lot of structures, that's okay. You can just listen to my words. In chemistry, when something is anything, we call it R. So what this is saying is this looks like this, and then there's other stuff with the molecule on the other side. And so there's two main types of chemistry, the sulfonic one and the non-sulfonic one. And so we started with the left, these 8 carbon ones. They're like perfectly persistent, bioaccumulative, check all those boxes of bad things. So they were done. They were done through different regulations and phase outs. There are some exceptions still. But let's think of it as what do we do next? Well, they did the exact same thing, just shorter. So maybe you can tell these are smaller. These are 4 carbon instead of 8 carbon. That changes nothing about the reactivity. The persistence is exactly the same, but what it did change was the bioaccumulation. Turns out it didn't really change the toxicity either. So this is what we would call a regrettable replacement, right? Not a good replacement. The other thing they did is, if you can see here, there are O's in the middle. That actually doesn't change the persistence or toxicity either. But again, it makes it more water soluble and less bioaccumulative. And so I'm going to say these are like, at first I thought these were better replacements, and now finding out, especially like this one down here, pretty toxic. So just because it doesn't build up in our bodies the same way doesn't mean it fixes the other problems that we're worried about, right? And so actually this was a direct, from this to this was a direct replacement in the production of Teflon, for example. It was like a swap in. So like I said, because of this regrettable replacement sort of trend, the discussion is like, well, let's ban them all, right? And of course that's being debated. So this is also a crazy structure, but I want to point out, and this goes to Valerie's question earlier, these are like a lot of different structures and some crazy chemical structures, but most of them break down to those carboxylic and sulfonic acids, like that PFAS and PFOA, but different chain lengths. So like even some PFAS do react in the environment. Microbes can react with them, oxidants, all these sorts of things. Some of them react really slowly, some of them react faster, but eventually they're all gonna mostly get stuck at these ones that don't degrade. So this is, you don't have to look at this. So how do they get from what they're supposed to be used for into the environment where we're concerned? So I'm gonna start with direct emissions, spills, right? Firefighter training I mentioned. When they were pesticide additives, that's directly into the environment. Wastewater treatment plants, and so the reason they're coming from wastewater treatment plants is wastewater treatment plants do a great job at removing all the nutrients we send to them and lots of other things, but they are not designed and not able to degrade these chemicals. So they're not necessarily, like, it's not the wastewater treatment plant's fault, it's just a spot where it's entering the environment, is how I would say. But of course there's room for improvement there because we bring everything to the same site. And finally, the chemical industry. So that can be making PFAS or using PFAS. And transport, right? We've talked about this a lot, but ocean currents, air masses, yeah.
So this might be completely outside your realm.
That's okay.
But is there, I know that water treatment plants are also an issue with microplastics. Is there an opportunity for those two, like the PFAS side and the microplastic sides, to kind of work together to find solutions at those water treatment plants, or is that two completely different problems?
Yeah, I would say that's a good question. So the thing about removing microplastics is it's usually a physical removal, from my understanding, whereas PFAS can be physically removed. So when I say physically remove for PFAS, I mean like get them to stick to something and then take that thing away. But I think people would prefer the break them down method. Realistically, it's usually a combination of both, because if you're going to break anything down, sort of like pre-concentrating it, so getting it all stuck on something that you can then take to a facility if your facility can't do it, or if you can do it in line, that would be good too. I think there are, not a remediation expert for sure. I think the challenges are different, but it does fall into that category of like this is not what it's designed for. And another thing to point out is like the concentrations coming out of the wastewater treatment plant, they're still low in the scale of things, right? Especially when you're comparing to the things that the wastewater treatment plant is designed for. Like we're worried about really low amounts of PFAS. And so working really low, and I have some numbers coming up, working really low can take a lot of energy and like energy in every capacity and facilities. But yeah, good thought. One more thing I wanted to point out that is a way that unfortunately PFAS can get transported is wastewater treatment plant sludge reuse. So the nutrients from the wastewater treatment plant sludge are very good for fertilizing farms. However, they carry everything with them. So there is a lot of concern, and there's been most of the work has been out of the Northeast US showing uptake into crops. That can be quite concerning. So it depends on the wastewater treatment plant and what's in their sludge before it's being applied. Okay, and so point source contamination that like we know and can like target in a way that's easier than maybe the wastewater treatment plants, airports and army bases. I did not include it, but there is, it's sort of sad. If you look up like known PFAS hotspots in Canada, it's just a map of airports and army bases. But it's because nothing else is looked at. It's like, well, of course that's where it's going to be because we know that they use the special foams and have for 30 years every year. So it's actually a weakness in our spatial coverage of Canada, I would say. So I didn't include the map because honestly, it's not that interesting. But in the US, they have much more data because they've been doing a lot more measurements. So it takes a lot of work to do these measurements. Fluoropolymer manufacturing plants, those are some of the really historical ones. My note, PFAS have never been produced in Canada. They've been imported and used, but we've never made them. So we don't have some of these like horrifyingly contaminated sites. Like there's really bad ones in North Carolina and in West Virginia. Have you seen the movie? I could tell. Okay, good. There's a documentary called The Devil We Know, and then the movie's called Dark Waters. It's with Mark Ruffalo is in it. It's really good. I recommend it.
You can probably rent it from the library.
Yeah. Shout out to the library. Dark Waters is the film. It's called The Devil We Know, and it was on I saw it on Netflix. I don't know if it's still on there. It's the same story. It's just one's a documentary and one's a film, a Hollywood film. But the issue there is they were making Teflon, and all of the workers had really bad health effects, including their children. And they discharged waste from the factory into the river, and then the cows drank at the river, and the cows all died. It's quite horrifying, actually. So it's not good news, but we just don't have that in Canada because we never made it. So we don't have some of those same horrific problems that certain parts of the US and like Belgium has some really bad sites too, for example. Another reason North Carolina sort of double slammed is that, I don't know if you knew this, but North Carolina has a huge sofa industry and upholstery. And because all of those coatings that go on textiles, so you imagine like a textile factory, like maybe I don't really know how all the industry works, but they apply the PFAS coating there, right? Maybe they don't weave it. I'm not really sure. Maybe they weave it too. But they buy the PFAS and put it on the textile. And so huge waste issues as well. Like, and right, like I feel like, when you can see emissions, like I can see the flare from the refinery from my office. I can like see something's happening, right? Or if you see something come out of water that's like brown, you're like, oh, that's dirty. PFAS are colorless, right? And so the water might look clean. I've been to a beautiful site in Southern Ontario that's downstream of an airport. It's a nature reserve, and it has some of the highest PFAS concentrations in Canada. And the reason it was found is because they thought it could be their clean site to compare to an industrial site in Hamilton. So they went to the Hamilton Harbor, if anyone knows Ontario, And then they went to the nature reserve, and the PFAS concentrations in the snapping turtles that they measured were like 1,000 times higher in the nature reserve. And then they realized it was because of the airport at the headwaters of the river that turns into a lake. So that's when in Canada, what we know is army bases and airports. There are other predictions that can be made where PFAS are used based on industries, but not the same as in the US. And then humans, this is sort of just, I think I've actually talked about this, but we as humans get exposed through our air a bit. That's not really well understood, but drinking water, consumer products, and they include transfer to infants, so that is known. Maternal transfer is a thing for PFAS. So current PFAS regulations in Canada, and I want to emphasize that there's a lot in the pipeline that we don't know what they're doing, but that they've committed to doing things. So this is I basically quoted this from the website. So with some exceptions, prohibit the manufacture, use, sale, offer for sale, so you can't advertise selling it, and import of the following PFAS. So I've been talking about PFAS a lot. So the wording is PFAS, it's salts and its precursors, because you can buy this with potassium or sodium, so it's a holistic cover everything. And its precursors, like where I said that are. So it's saying anything that breaks down to PFAS, also banned. That's good regulation in Canada. That's not the wording in everywhere. And same for PFOA. So PFOA, it's salts. So if you buy it with a sodium, that's included. And its precursors, so things like this. Again, super holistic. And another thing Canada did is it said that anything that looks like PFOA but's bigger, they call that long chain perfluoroalkyl carboxylic acids, is included. So this is C8. If there's another carbon or another carbon or another carbon, all of those are included because those ones bioaccumulate. And so that is the current regulations, and that will change pretty soon to include other things. But this is where we're at right now. So there are drinking water regulations. These are new, and you know what happened? This is really annoying. It didn't sync. I changed this to recommendations. Drinking water recommendations. It does mean something different. I remember that change. When I said it didn't animate, that's the same change I made, and it must have not saved. That's fine. So these are not enforceable. This is a recommendation. And so what they've done is Canada has taken the approach of a list of 25 PFAS, right? They're like, these are our most concerning. We've prioritized these. And when you add up all their concentrations, we suggest below 30 nanograms per liter, which is parts per trillion. So not enforceable, but a recommendation. To compare to other people, European Union, so all of Europe has one together, they do 20 PFAS at 100 nanograms per liter, so theirs is higher. So we do 25 and 30. They also have one which they call 500 nanograms per liter for sum of all PFAS. I think that's hard to measure. I don't love that, I will just say. The US EPA, which, we'll see what happens. But right now, they have very low limits on just those two compounds. And so for PFAS and PFOA, each of them can be 4 nanograms per liter is the recommendation. So I would say that, I think we're pretty comparable. So both of those are less than 20 nanograms per liter. So that's not like adding together, we want less than 25. They don't say the number, they just say less than 20. I think that's pretty good, right? It's not less than that 4 that the US said, but that's pretty new and people think it's shockingly low. So this is below their reporting limits, I would say. And again, there's no legally binding amount. So I'm pretty happy that we are below this. I think that's good. So I think unless there's something weird between your house and the distribution line, right? It's possible, right? But I think our water here is good, so we don't have to worry. We are not living in a site that's heavily contaminated. Okay, I've been talking so much, so I'm going to go through my research quickly because this is more interesting. Because one thing I want to teach you about this idea of essential use, and I've sort of been getting at this, and I like this paper from 7 years ago now. Do we need this application? And are PFAS the only way to get that application is the question. So they group things as non-essential, substitutable, and essential. So substitutable means we need this function, but we can use a different chemical. Non-essential means they don't think the function is required at all. And so it's the application that's essential, not the chemical. So you cannot say a chemical is essential. You can say an application is essential, and we only have one chemical that can do it right now, right? And I think that's really important to think about. This table is very hard to see, but I'm going to try to just tell you a few things. So the orange means non-essential. Personal care products, including cosmetics. Ski wax, so really high performance ski wax. It was like banned from the Olympics. A fun, easy care clothing. So the authors think that we do not need clothes that don't need to be ironed. We can just iron them. Fair, right? We have steamers now too. And then I want to point out the essential ones, and I highlighted some here. Military and medical applications, and right now, there's no substitutable for these like chloralkali processes. It's like a very important industrial process. And then the rest are like, they can't decide exactly which one it fills. So we'll skip that for now. So I think this is a really useful framework in general, especially for those interested in sustainability. Like, do we need this application? If we do, and the chemical we're using is bad, like, right now we have to use it, but we should be driving for solutions that use better chemicals, right? Okay, so why do we need to keep studying them? Like, why am I doing this? Like, if we know it's bad. So it's unfortunately going to be a long-term problem, right? They last a long time. They're going to be in the environment. And another thing to remember is that, like, let's say you bought a couch 10 years ago and it has PFAS on it. It's going to keep releasing into the environment slowly, maybe in your home, and then it's going to go to a landfill, and then it's going to keep releasing, right? So we're not just done with these things. There might be stockpiles in some factories, stuff being sold. So it's not like illegal to sell things that have PFAS in them already. It's like you can't, if it's already in the store, what are you going to do, right? So we will keep having emissions of PFAS. They'll go down for sure, right? It's not going to keep going up. But and another thing that motivates me is like, what can we learn from this, right? Studying how problematic chemicals behave can teach us something maybe for remediation and how to design greener chemicals. So I don't make chemicals, but I hope that the output of my work can teach my colleagues like, oh, don't do this. That'll be a problem. Okay, so I'm going to tell you a story about one PFAS, but it's really going to be about more PFAS because they're interrelated, of course, right? My God, these colors are so bright on here. This is trifluoroacetic acid, or TFA. It looks a lot smaller than the other ones we've been looking at, right? So I'll remind you, fluorine, useful properties. TFA is increasing in concentrations in what we call time-resolved samples. So samples that can give us insights into history. So ice cores, when you dig them out, the lower ice is older than the newer ice. TFA is increasing in the newer ice. Same with archived leaves. So they took leaf samples and threw them in the freezer every year. And then over I think it's like 40 years in Germany, TFA was going up. And groundwater that hadn't been exposed to air. They can do all sorts of aging and increasing there. I would call this a forever chemical. I'll give you that. It's got no known degradation. It's generally called a PFAS. What's interesting to me, because I like these transformations, is TFA is mostly not used itself. It is used a bit, but it mostly is because there are many fluorinated chemicals, and we live in an oxidizing world, and they degrade to TFA. So we use all sorts of chemicals, they enter the environment, and then they react to form TFA. So interesting, but complicated. Why should we care? Concentrations are increasing. We don't have any way that they decrease naturally. There is some toxicity information, but it's limited. We're learning more. And I think we should remember the precautionary principle, which is if something, is building up, we should be proactive. So the industry folks try to argue that TFA is natural. And their main argument, I'm going to say, is that they're like, there's too much in the environment. It doesn't make sense based on what we know. I think that's a bad argument. And so during my postdoc, we did this sort of deep dive and said, you have to prove how something's natural. Like, is there a microbe that makes it? Like, you can't just be like, the math doesn't add up, therefore it's natural, because like we can't do these for many chemicals in the environment. So we said it can be explained by poor analytical methods, so bad measurement techniques, or challenging, let's say. Small amounts of environmental sampling, so they would measure only a few sites and then multiply like by the whole ocean, for example. Understanding of transport, and my favorite, poor understanding of secondary formation, so this transformation product bit. And so I will say that a lack of understanding all environmental sources doesn't mean it's natural, but we need to figure out where it's coming from. Why is it increasing, right? So this is some work from my postdoc, and we were studying TFA in the atmosphere. So it does exist in the atmosphere and the water. It is unique and interesting in that way. And so the hypothesis is that chemicals that are volatile, so they're in the atmosphere, get oxidized to make TFA. And if they're oxidized and require the sun, we should see some trends if we can make quick measurements. So, you can tell by the masks, this is COVID era. We collaborated with Environment Canada in Toronto, and we made really fast measurements. If you can make fast measurements, you can correlate it to time of day, all these sorts of things. I'm going to show you some crazy data, and then I'm going to show you a different way that makes more sense. It's sort of hard to see, but we did winter and summer in 2022. The black is the concentration of TFA. So you can just see it looks like noise, but it's because we're measuring so much and seeing the changes. I will joke and say, can you squint and see the daily trends? The orange is the sun. It's really hard to see on here. So this is hard to look at. So what we do is we take all this data and we average it to time of day. And I'm just going to show you the summer. It's sort of hard to see on the screen. So this is noon, right? So I have the summer and the winter. The lowest concentration, if we average all of our data, so we're simplifying it, is at, 6 a.m., 5 a.m. And then as the day goes on, it increases and then it decreases. And so we correlate with the sun and some other chemicals that we know require the sun to be formed. Ozone, formic acid, we have those measurements too. It did not correlate with wind direction, which could tell us a direct emission, and carbon monoxide. And so what we found from this study is that in the air in Toronto, most TFA is formed as a product of these reactions with the sun and oxidants, not that TFA itself is emitted to the atmosphere. So we don't know from this what it is. We have some ideas, but this is the sort of research we can do where our experimental observations of the real environment can give us insights into processes. And also for context, like sometimes people think because it's a city, maybe there would be more direct pollution of using TFA and sending it to the atmosphere. And then I'm going to show some work that, sorry, this is small, we've done here at the U of A in my group. So I'm studying it now in the water, and I'm studying how the sun now interacts with some chemicals that are dissolved in water. So when I showed you that photo like an hour ago in my reactor, and I was like, it's like if it's at the top of a river. So these are pesticides and pharmaceuticals, and I've highlighted this part of the structure that I want you to look at, and you can see they have CF3 and then this ring, right? I will point out, technically Canada considers these PFAS, but they consider pesticides and pharmaceuticals separately. We regulate those completely separately. So even though there's this broad definition of PFAS, they sort of take that out and say it's a different thing, which I think is a good approach. Just so you know. And so my question is, can these react to form TFA? And that might not be so obvious looking at these for you, but as a chemist, I can see a possibility. And so what can happen to these in the environment? These are our pharmaceuticals and pesticides, and these are just some examples. They can either persist themselves, right? Maybe they don't break down. And if we're focusing on the fluorinated part, because that's what I'm really interested in, they could undergo defluorination, so those carbon-fluorine bonds can break and it can release fluoride. That's what we want. We want those bonds to break when something is in the environment that we don't want in the environment. And the other option is like, can it make some TFA? And that's what I'm curious about. So all those structures on the left, where I circled them, we know those bonds can break actually. And so, all right, you can see like we're interested in these structures, and I'm just actually gonna start by studying these. I'll show you on the next slide. So we're just taking that simple block that we know will break off in the environment, and we're gonna zoom into that and study. So we want to look at where the OH versus the CF3 exist on the structure impacts the reactivity. Okay, then we actually wanted to look at what happens in the dark. So in water, when there's no sun, we actually saw some reaction. I added one more chemical because some of those pesticides especially have this sort of structure to them. And so it looks like this one, but has a chlorine, right? And so do they produce fluoride? Do they fall apart to make fluoride without the sun?
And when you say dark, do you mean it's nighttime, or it's like the depth in the water that it is then dark?
Good question. I mean, doesn't need sun. Okay. So I guess it could be also light, but like the sun is not a factor. Okay. So the way we do the experiments is we put them in a drawer. Sophisticated. But the implications are that if it was in a river with sunlight, both reactions would happen at the same time. So it's like two different mechanisms happening. And the rates are dependent on different things, but that both can happen. So this one, it does not fall apart and make fluoride, but the other three do. And this feels counterintuitive to some people, but it is really pH dependent. So I told you I wasn't going to talk about rates for the top, but I'm going to talk about rates or speed, how fast is this happening, at the bottom. And so we see a difference around pH 8, so that's a little alkaline. Usually our surface waters are a little acidic, but they can be a little alkaline too. And this is me trying to simplify it. So big means faster. So when it's less than pH 8, this is fastest, then this one, then that one. And when it's greater than pH 8, these two just flip. So the rates are slower when it's more acidic, which is generally more relevant, so they don't fall apart super quickly. But it is really interesting. We want to understand, like, you know, why do some of these just break? Because everyone always says carbon-fluorine bonds, they don't break, they last forever. Well, not when you've got this configuration of the structure. So that's also what motivates us. And we've published 2 papers on this, and the other citations are some of the really old-timey 1947 papers that motivated this work. Okay, so what are we doing now with this? Way more, right? So I showed you a few chemicals. We want to build sort of like a library, like every relevant structure. Does it fall apart under these conditions? Does it make TFA? So here we're learning 2 things from the same experiments. Does it make a contaminant we're concerned about? And can we understand how chemicals break down, right? So I'm really interested in both. So we're gonna study all these. I mean, we're basically doing it right now. I just need to write the paper. And then we're also going to study some real chemicals. So insecticide, pharmaceutical, herbicide, antidepressant, and try to see, you know, can we sort of predict what happens to these based on the simpler building blocks? So sort of summing up this study, we're working, like I just said, to study more of them, more systems. I want to know more about the biodegradation and human metabolism too. And so some of them we found do sort of persist. Spoiler, I haven't published that. And that's not good because those are designed to be biologically active, right? So we don't want things sticking around that are biologically active. And so can we inform the design of any sort of organofluorine, including PFAS, where those CF bonds aren't forever? And so can we use those properties of organofluorine that are useful without the major persistence problems? It's a huge task. I think not the same level as PFAS, but maybe some of the other ones. And I just want to remind you, like the goal, and I haven't used this word yet today, but it's mineralization. So we want everything to break down to the smallest building blocks that exist. Carbon dioxide, right? Like nothing can really be smaller. And we want them to return to the geochemical cycle. And so we don't want to be making things that aren't there naturally. And I will say that this question will keep me busy and motivated for my career. Okay, any questions about this? And then I was going to tell you about some other, I am watching the time. I was going to tell you about some things we're working on that are related to this as well. And then we could do questions at the end if you want. So I talked a lot about why we're worried about Arctic contamination, right? Both for the people there and the fact that it means the globe is contaminated. So one thing we're doing, collaborating with Professor Ken Jeffries, is looking at PFAS in these soft shell clams. This is a clam on a trowel that Ken took a photo of, way up in Nunavut, so Iqaluit, and then around the bay as well. And we have a number of sites. Oh, I'm falling over. And we can look at these clams that are both in the Iqaluit area, in the more open ocean area, and downstream, I guess, of a melting glacier. And so the thing about the glacier melt is the question is, as these melt, are they releasing older contaminants that were trapped, right? So something was banned 20 years ago, and it reached the Arctic 30 years ago, and now that ice is melting, are we getting a release, right? So these are our big, that's a way that climate change and contaminant sort of research, they tie together in many ways, but that is one of them. Are we releasing old contaminants? Another thing is that these are important food sources for certain times a year when the tide is low enough. And so, I mean, I can tell you right now, they look pretty clean, which is good because we don't want people to eat contaminated food. Another really exciting thing I'm doing is collaborating with Alison Crisatello, who's a professor at U of A. Maybe you've heard of her. She's the ice core scientist. And so she has collected a really cool 150-year-old ice core for me. So she studies she studies like climate and carbon dioxide. So she has this crazy deep, like record-breaking ice core that goes back millions of years. But the chemicals I'm interested in have not, we don't need to go that far, right? So 150 years is actually extremely old for looking at these sorts of chemicals. And I'm really excited to look at that. And so that gets into the remote, like we can look at global trends over time. But we are not touching those samples until our methods are 1,000% perfect.
When was the first PFAS, I guess?
Oh yeah, I don't think I talked about that. It really started being produced more in like the 40s and then used more in the 50s and 60s. Yeah. The first time, this is nerdy, but the first time they realized that we didn't just have fluoride, like fluoride that we put in our drinking water that's like good for you at low amounts in our body. So they saw that there was fluoride and organofluorine, right? So PFAS and other things like that in this incredible paper from the 1970s that took so much work. And I will just tell you because I care about measurement science. So right now, if we want to measure PFAS in blood, we can take less than a milliliter, extract it in the lab, do a little cleanup, and easily give you concentrations of 40 specific PFAS. It might not be there, right? You might see 6 of them, but you can look with quite good sensitivity. That's pretty standard. So another thing we're doing, I talked about those pesticides and pharmaceuticals. We want to study them and TFA in the environment to see if there is a relationship as well. And so I'm collaborating with Professor Mark Hansen at University of Manitoba, Dr. John Chalice, who's at Agriculture and Agri-Food Canada. He's a pesticide chemist there. And really coolly, the Lake Winnipeg Foundation. And so they have all these volunteers that sample across their watershed in Manitoba at 100 different sites. So we're gonna do a preliminary one this summer, and then we'll decide where to go sample more because we can't sample all those sites all the time. And I did get at this that we're studying the release of PFAS from textiles. So I'm collaborating with Professor Rachel McQueen, who's at U of A. She's a textile scientist and sustainability person. And we're interested in looking at, are there PFAS in textiles if you just buy some fabric at the store? How can they be released? And lots more questions about textiles, actually. There's a lot to think about. Finally, I just wanted to show my group. This is us in the summer. I'm at our picnic, which is why I'm wearing shorts. I want to thank, of course, all my group members who work hard. We have great collaborators as well. I want to thank Valerie and Carlo and all of Future Energy Systems. They fund some of my research as well and give me cool opportunities like this. And then, funded by NSERC, CFI, and U of A. And really thank you all for coming. I've been having a lot of fun, and I have time to chat. So if you have any questions. Yeah, okay. Thank you.
I've heard the term hard water. Is that related? What is that?
No, hard water has to do with the calcium, right? No, it's different. That's because we get the residues on our kettle or shower or whatever. Yeah, it's mostly more harmful for your pipes than you, I think.
And also I heard something about there being a teaspoon of microplastics in your brain or something like that.
Mm-hmm.
What is that about?
Yeah, great. Yeah.
You know what would be great? Our next talk is actually on microplastics.
Who's giving that one?
Kira, one of our energy explorers, one of
great.
our grad students, will be here on February 25th to talk about microplastics.
Yeah.
So might be a great person to come back
maybe
to
we'll
and
save
ask
that one.
those questions.
Yeah.
Yes.
Yes, I was a lot.
But knowing that it's present and its severity, it's PFAS, everything that's using it in, why continue using it? It's for the money, you mentioned briefly, money. So.
Or why are they being used at all?
Why do they still continue if they know the severity of it all?
I actually think a lot of industries want to get out of it. They do not want to be involved in this. I would say the industries that are pushing back the most are, I'm going to call them the refrigerant and heat transfer fluid industries. So they really, I'll explain to you what I mean. If you have a car that is from after 2018, 2019, your coolant in your air conditioner is probably called R134YF. If you have a car before that, like me, it's probably called R134A. So they have been changing they call them F gases sometimes, but they're really these fluorinated heat transfer fluids because they used to use CFCs that ruin the ozone. Then they switched to non-chlorinated ones that just have fluorine, and they realized they're pretty bad greenhouse gases. So they fixed one really, really bad problem, and they have another problem. So now they've switched to other ones that don't last as long in the atmosphere, so they can't have as much of a greenhouse gas effect, but actually they make TFA. I just didn't want to get into that today. There's too many things. And so that industry is really saying, we have pivoted, we have fixed some serious, serious problems, and you're still coming for us, is sort of, that is the vibe that I get. And so they are trying to say, we are so different. We are nothing like PFAS. Our structures are so different. To be fair, those aren't toxic, but there are other concerns. And so they don't want to be called PFAS because then they're we're going to fall in this group. So that is the biggest, it's that and the fluoropolymers. So Teflon. There's really important tubing for important industrial, medical, actually laboratory applications where you need literally a tube. If you're going to pass something through a tube, you need stuff to not interact with it, not stick to it. Medical, it's not going to go away for medical. There's no way Teflon or PFA tubing or it's
Benefits more
the user. It benefits the user, and there is nothing that compares for that. Again, if there was some other material that had those properties, they would sub it in. And people are working to innovate that. It's going to be hard. So I think that's the main thing. The other one, the foams for firefighting, and I did not talk about, but like firefighter textiles, they need to be oil proof, right? You can't have oil coming through. And they also need to be breathable so the firefighters don't overheat. So that is technically very challenging. And from my understanding, it's a little beyond my expertise. For both of those cases, there's debate on if the non-fluorinated ones meet the safety requirements. And so they've started using non-fluorinated firefighting foams in, I think they're allowed in certain countries in Europe, but not 100% sure. People are just when it comes to the safety issues, there's a lot of fear in changing, understandably so, right? So I would say most people or most industries, they want to put that green sticker on there, right? And there's been a lot of drive from the consumer. So there's like within the textile world, there's all these companies that have signed on to like, we are PFAS free, or they'll say we are PFAS free except for this one like very high performance jacket that needs to have PFAS, or by the year 20 whatever, we're going to be PFAS free. So I actually think that the change is coming from social movement at this point. It didn't start that way, but even I've been studying PFAS for like 13 years, I think. What year is it right now? 14. And since I've started studying PFAS, I've seen it change to be a much bigger social movement.
About what do you think it would take for them to limit the usage of the PFAS? And you mentioned like the awareness that people haven't studied.
Yeah, and I think our government is doing like a pretty good job with the way they're approaching the regulations in Canada. Like I said, like this, like including like and precursors too. But it's the data that goes into those decisions, like they need a lot of data. And so that's like I was saying, like I have a grant that's from the Chemicals Management Plan of Canada, and they basically sort of put out these calls that are like, we need more information on like these classes of chemicals, apply for something related to that, because as our government, they can't, like they need good science to inform there. Unfortunately, we have a reactive system, right? Not a proactive system versus like I got at this earlier, like pesticides have to put in way more studies before they're approved because they are sprayed into the environment. When you make a new industrial chemical, it's like, you have to do some now, but we also have this backlog of all the ones that didn't have to do anything before. So, yeah.
So it's a sign right there that they heightened the level of scrutiny based on the direct impact and effect on the environment or human, like their health.
Yeah, and so now they're like, we need to do something. Yeah. Yeah.
This is a lot even than that.
Yeah.
Was there hands over on this side? Okay. Well,
I can talk after, but we can formally end. Thank you all. This is
give
great.
another round of applause.